Look at the Milky Way. Hundreds of billions of stars, countless potentially habitable worlds, and yet, silence. Where is everybody? Some astronomers suggest a terrifying answer to the Fermi Paradox, that civilizations eventually sever their own access to the stars, marooning themselves on their homeworlds long before they can cross the void. We might be doing exactly that right now. Over the last few decades, we've launched thousands of satellites, wrapping Earth in a dense, chaotic web of orbital traffic. The dead hardware and shattered rocket bodies accumulating in low Earth orbit represent a literal, physical barrier that could end our future as a spacefaring species. The modern global economy relies on a highly synchronized network of active satellites. They route our communications, guide our navigation systems, and track our weather. Over 80 different sovereign actors and private companies are actively participating in space right now. Launching hardware into orbit is immensely profitable, and the rush to claim these orbital slots is accelerating. Companies and governments routinely abandon their broken hardware in the sky because there is no immediate financial penalty for leaving a defunct satellite in orbit. It makes perfect financial sense for an individual operator to save money by doing nothing. Yet the shared resource of low Earth orbit is completely finite, and treating it like a limitless junkyard steadily guarantees its destruction for everyone else. In 1978, NASA scientists Donald Kessler and Burton Corpellet predicted that as we launched more objects, the orbital debris environment would eventually be controlled entirely by random, violent collisions. Low Earth orbit is an incredibly congested highway where objects travel at extreme speeds, exceeding 30,000 kilometers per hour. At those speeds, a collision between dead satellites vaporizes the hardware into millions of untrackable shrapnel pieces, turning them into hypervelocity bullets. This sets off a mathematical chain reaction known as collisional cascading. One collision creates 5 fragments. Those 5 pieces hit other objects, creating 50 more, escalating rapidly into the thousands. We are rapidly approaching a critical tipping point. Soon, these new fragments will accumulate much faster than Earth's natural atmospheric drag can pull them down and burn them up, locking this runaway chain reaction in place. Modern stochastic models, simulations that use probability to predict complex environments, point to a scenario called the economic Kessler Syndrome. Space doesn't need to become a solid wall of flying metal to ruin the industry. Long before that happens, the sheer mathematical probability of a satellite getting destroyed will cause expected profit margins to vanish as insurance costs skyrocket. The window for safe operations is shrinking fast. Researchers track a metric called the crash clock, which measures the time we have to recover from a widespread disruptive event. In 2018, that clock sat at 121 days. Today, it has collapsed to just 2.8 days. During the early days of spaceflight, operators assumed orbits were so vast that objects would simply self-cleanse over time. Relying on those assumptions, we saturated near-Earth space without planning for the long-term consequences. If this risk curve continues, the realized financial value of low Earth orbit drops exactly to 0. Space becomes economically dead long before it becomes physically impassable. To figure out how to keep orbit usable, engineers use the Kessler stochastic model to evaluate different mitigation strategies. Space agencies are actively testing active debris removal technologies, launching capture missions where a small probe matches speed with a dead satellite, fires a net to catch it, and then deploys a sail to drag it into the atmosphere. While these retrieval missions capture the public's imagination, the model's data points to a far more effective solution: population management. Population management doesn't require futuristic inventions. It is simply the rigorous, regulatory enforcement of a single rule. If you put a satellite into orbit, you must safely deorbit it the moment its mission is complete. No amount of cleanup technology can outpace the math of collisional cascading. We have to correct our legal and behavioral frameworks first. We are finally starting to see movement. International frameworks, like the United Nations Guidelines and the ISO 24113 engineering standards, now explicitly detail how to limit the time a dead spacecraft stays in orbit. And regulators are putting teeth into these standards. The Federal Communications Commission recently mandated a strict 5-year post-mission deorbit rule. Because this applies to anyone wanting to serve the massive U.S. market, it effectively forces a global standard. We have reached the point where we either strictly govern our orbital commons right now, or we accept the mathematical certainty of inaction. If we fail to clean up our skies, humanity risks becoming the very answer to the Fermi Paradox we fear, a civilization that marooned itself on a single planet, ending its story before it could reach the stars.